Uh, hey everyone, this is going to be part 4 of our Echidna workshop series, which is using Echidna like a pro. Today we're just going to continue right where we left off, and yeah, I'm super excited for this workshop. I hope everyone can learn a lot. That being said, let's just jump right into it. So, we've had some previous workshops before, like this last week, where we talked about the Uniswap code base and we wrote a couple of tests. Today, we're largely just going to be building more on top of that, getting into some more complex testing, investigating other contracts. So, if you haven't seen that workshop, I'd highly recommend it because if you're not very familiar with the Uniswap code base or Echidna already, then this workshop might be a bit more confusing to you. Also, we've had some more beginner-friendly workshops on how to use Echidna. My colleague Anish did a really great job explaining like the basics of Echidna and using Echidna on a fixed point math library. I'm not going to explain too much about using Echidna. I'm just going to get right into it. So if any of what I do is confusing today, I'd highly recommend checking out those beginner workshops as well. And this is going to be the last workshop I'll do, but next week we're going to have some interesting workshops going on. I'd highly encourage everyone to check them out. They're a bit more advanced, so I'm sure that if this content is interesting to you, you'll get a lot out of it. So I'm the same person that was here last week, but I'll just briefly introduce myself again for those who don't know. My name is Justin. I'm a security engineer here at Trail of Bits. Who is Trail of Bits? Our job is to help developers build safer software. So we're pretty research and development focused. We use a lot of the latest program analysis techniques, and open source software is kind of at our core. We have many open source tools like Echidna, obviously, Slither, Tealer, Amarna, and much more. I'd highly encourage everyone to go check them out and use them in developing contracts or whatever you need. So yeah, I'm gonna give a pretty brief overview of what we did last week, just so that everyone who was there can kind of get back up to speed, jog their memory. Again, if you haven't seen last week's workshop, I highly recommend it because we're just going to be building on top of it. And even though I'm going to give a brief recap, it's kind of hard to recap something that was an hour and 15 minutes long in like 5 minutes. So that being said, let's just jump right in. We're going to recap what is an AMM, how swaps work, how liquidity provisions work, the actors involved, and then we're going to go over the core contracts and the test that we wrote last time. So to answer the question, what is an AMM? An AMM, as opposed to the traditional order book model, we talked about that last time. And in an order book model, the price is just based on the bid-ask spread. However, here there is no order book, and the pricing is just based on the pool's liquidity formula. And this very simple example is the one that we all know and love: x times y equals k. That's Uniswap's liquidity formula. And the price is calculated as a ratio between the two assets. The core idea of an AMM is that exchanges keep a pool invariant constant, and AMMs have certain advantages over order books, like, for example, they don't need external parties like market makers or takers, and they're a lot simpler to do on chain. So let's talk about how a swap would work on an AMM. We saw this picture last time. I'm just going to briefly summarize it. So let's say a trader wants to put in swap 3 of token A for some amount of token B. Last time we actually derived mathematically how much he would get out. The answer is 1, as you can see by the pretty picture. The pool starts at a certain amount. There's a certain amount of token A and a certain amount of token B. And since we added some tokens and removed some tokens to the pool, we changed the reserves, and that affects the price. So as you can see, you get a new price after the exchange happened. And the key power of an AMM is that we can always guarantee liquidity, but we're just going to get continually worse and worse price execution. So we also talked about liquidity providers. These are the people who actually, you guessed it, provide liquidity. They provide a ratio of certain tokens to the pool, and then they get minted the special LP token, which represents how much liquidity they provided. The initial provider sets the pool invariant, which means they set the token price because the price is a ratio. And to get these tokens back, they need to burn those LP tokens. The reason that anyone would do this is not only because it enables swapping, but you earn a fee. Remember this 0.03% fee on every transaction. That fee goes towards liquidity provision. It's a passive way to make money. So here's a really easy picture explaining what goes on. We're going to put in 3 of token A, 1 of token B. That's our ratio. And we're going to get out a certain number of pool tokens. Those represent how many tokens of the ratio of tokens we put in and how much of the pool that we own. So as you can see, we get out 12.4 pool tokens. And the key to note here is that more liquidity increases the low slippage area. So the more liquidity there is, you can see in that green box, you're just going to move around that green box. And the more liquidity, the smaller the green box is. So you're going to get better price execution and therefore low slippage. Again, all of this was explained in pretty great detail in the last workshop. But if there are any questions, I'll be happy to take them now. Now, questions? All right, so I'm going to start talking about the actual code, and we went over the core contracts, which are the factory and the pairs. The factory, as we saw, is just to create the pairs, and the pairs, let's look into them. So the factory, as we can see, what does it do? Main job, create the pair, the create two, initialize them, and then populate a mapping. The pair, we went over all the logic, and we covered this mint function right here. We talked a lot more about it in detail, about what it does specifically. I'm just going to summarize. The key here is that we get the balances, we get the reserves, we calculate the amounts to mint, and we look at the total supply. If the total supply is 0, we're going to mint liquidity tokens according to the geometric mean of the two amounts. As you can see, amount 0 times amount 1, take the square root of that. Otherwise, what we're going to do is we're just going to mint the ratio of tokens in the pool, which represents the shares of liquidity that you own. And then we're just going to call this update function. That updates the reserve, that syncs basically the balances to the reserves and updates the price accumulators. And yeah, that's all that we covered last time about the factory and the core. And we also wrote a basic Echidna test for it. So we have the user. Since we're doing external testing, we're going to simulate, this contract simulates an EOA. It just calls a target contract with some data. We have a setup contract, takes into test tokens, factories, pairs, everything we would need to test the system. One thing to note is I renamed this function from mint tokens to initialize. That way it's a bit more clear that it's only meant to be called once. However, the functionality is the exact same. And we can actually go and look at the Echidna test we wrote. So we have our preconditions. We set up everything. We compared the LP tokens before, the reserves before, and the pool invariant before. We transfer tokens to the pool. We call mint on the pair, and we assert some certain invariants. Again, all of this was explained in great detail last time. But if there are any questions about the code that you would like me to clarify, I'm happy to do so. So today, we're going to continue right back where we left off, which is testing swaps. Then we're going to talk a bit about the periphery. We're going to cover some more invariants, and then we're going to do some simplified end-to-end testing. This isn't really end-to-end testing because we're not actually testing every single function in the code base, but we are testing pretty much the entry point of the system all the way down to the core logic. So that being said, let's just jump right into it. So let's go back. Let's look at the pair. Hopefully, now that I zoomed in, should be a bit clearer. And let's take a look at this, where is it? Swap function. So there's this comment that says this low-level function should be called from a contract which performs important safety checks. We'll keep that in mind. And what parameters does the swap function take? Well, we have an amount 0 out, we have an amount 1 out, we have an address, and some data. So the two amounts, amount 0 out and amount 1 out, those are the amounts that we're supposed to be getting out from the swap. The address 2, that's who we're going to send the tokens to. And this data isn't very important, but if you're doing a flash loan, then this data is what the callback would be used. There's a reentrancy guard here, so it's not possible to reenter the contract. And now let's look at the functionality. So we are going to make sure that these two amounts, amount 0 out and amount 1 out, are bigger than 0, because we expect when we call this function, we should get something out. The next thing we're going to do is we're going to get the reserves, and we're going to make sure there's enough liquidity. So that's why we check that amount 0 out is less than the first amount, reserve 0, and amount 1 out is less than reserve 1. Otherwise, we wouldn't have enough liquidity to provide the swaps. Next thing we do is we check the to address to make sure it's not either one of token 0 or token 1. And here is something interesting that we do is we're going to optimistically transfer these tokens. So as you can see, if the amount 0 out is bigger than 0, we're going to transfer token 0 to the 2 address. And if the amount 1 is out, we're going to do the same thing. So if our checks are correct, this optimistic transfer should be fine, and we shouldn't be able to break the contract. Next up is just to check if the data is bigger than 0. We're going to do a callback. This is for flash loans. I'm not going to go too much into flash loans. If you're interested, I'd highly encourage everyone to check the Uniswap documentation. And then after we transfer these tokens optimistically, we're going to get the balances. Here, what we do is we want to figure out how much was actually put into the contract. So that's why we have these two variables, amount 0 in and amount 1 in. What we're going to do is we're going to compare the balance after we transfer the tokens to the old reserve minus the amount that we transferred. And if the balance is bigger than that, then the amount that was put in was the balance minus the reserve minus the output amount. This kind of represents the new reserve, while reserve 0 minus the amount 0 out was the old reserve. And if it's not greater, to prevent any overflows, we're just going to set it to, or underflows, we're going to set it to 0. Likewise, we're going to do the same thing for balance 1, and we're going to just do this check that makes sure something was sent to the contract. The next thing we're going to do is we're going to calculate these two things called balance 0 adjusted and balance 1 adjusted. What each of those represent is basically the new reserves minus the fees. That's why they're adjusted. As you can see, we take the balance, we multiply it by 1,000, and then we subtract the amount in multiplied by 3. This accounts for, if we go back here, and we go back to the 0.03% fee, this is how we account for that when we calculate the new reserve. So you can think of it as getting the new reserve minus the fee that was taken. And we're going to do the same thing for balance 1. And this check is the pool invariant check. Remember, you can think of this as the new reserve 0 with fees, the new reserve 1 with fees, and we're just going to multiply them together, which would mean this is like the new K. Then we're going to make sure that's greater than or equal to the previous reserve times each other, which is like the old K. And then since we multiplied by 1,000 here, we're going to multiply by 1,000 times 1,000. And the error gives us a pretty good idea of what it's checking. We're checking that the pool invariant does not decrease. So if all these checks pass, the next thing we're going to do is we're going to call this update function right here. What does it do? Well, we went over this last time, but the update function is really simple. All it does is just update the reserve with the new balance. And it also updates the price accumulators for the TWAP. But we're not going to get into that too much. So that's pretty much how the low-level swap function works. Are there any questions about this? No questions. Awesome. So now that we've investigated how the swap function works, we should probably think of some invariants that we could test, right? Well, one invariant to test is just transferring 0 tokens should net you 0 tokens out. And if you think about this, this is fairly evident because if you could transfer 0 tokens and get 1 tokens out, I don't know, you'd probably be watching this from like a yacht or penthouse. And yeah, if we put 0, we should get out 0. So how would we test that? Well, as we can see, there's this comment that says this low-level function should be called from a contract which performs important safety checks, but it's external, so we can just call it directly anyway. Maybe there could be a bug or something where there's some edge case with this amount or this amount, and we can call the swap function without putting anything in, but we can still manage to get something out. So let's go ahead and test that. This is the same exact Echidna test contract I had last time. We have this provide liquidity test, and I'm going to go right here. I'm going to create something called test swap. It's going to take in an amount 1 and an amount 2. So like with every test, we're going to have preconditions, an action, and some postconditions. So let's go ahead with some preconditions. Well, as usual, if we haven't been completed, let's just go ahead and call init with amount 1 and amount 2. Other precondition we need is that there has to be liquidity. Otherwise, the swap will always fail. So we're going to require balance. Balance of the user is bigger than 0. This specifies there's liquidity. And another thing we want to make sure is that Echidna won't accidentally call some exposed transfer function, or if we were testing it in a more complicated scenario, tokens wouldn't be transferred into the pool, because we want to test that if we don't put any tokens in, we're not going to get any tokens out. And luckily for us, if we go back to the pair contract, there is this sync function. And there's a helpful comment here on what it does. It forces the reserves to match the balances. So this way, even if someone does send something, we can basically call sync and it'll treat it as though we didn't send anything, because the reserves will get updated accordingly. So let's go ahead and do that. Awesome. Oh, this is pretty minimal, but we're testing something pretty minimal. So these are all the preconditions we need. Are there any questions about these? If there are no questions, I'm going to continue. So now that we have our preconditions, what do we need? Well, we need to call. So the same exact thing that we did last time. I'm just going to call this success1. It's going to be the user.proxy. What are we going to call? We need to call the pair contract. What's the data we're going to use? Well, let's do ABI encode with selector. The bytes that we're going to use are pair.swap.selector. Pair.swap.selector. What are the arguments that we need? We need amount 0 out and amount 1 out. We need who we're going to send the tokens to and some data. So let's do that. The amount 0 out and amount 1 out are going to be amount 1 and amount 2 respectively. We're going to send these to the user, and let's just have empty data for now. That's going to be our call. And now let's think a bit about what our post conditions should be. Well, there are a bunch of post conditions to test that we could test that would make this test a lot more like granular. And after the workshop, I'd encourage you guys to investigate how we could modify this, but I'm going to keep it very simple. What we should do is we should just make sure this call never succeeds. Why should this hold? Well, if this call, let's think about this. If this call succeeded, that means somehow we were able to get tokens when we didn't actually send anything to the pair. And that should not happen, hopefully. Maybe, we'll see. So we did the call, we did the post conditions. Are there any questions about this? Oh, oops, 1 second. Sorry, let me go back. Oops, why does it keep doing that? There we go. There is a question. Why is it better than simple out of the... Oh, the question is, why is Echidna better than simple out of the box boundary fuzzing? So there are a lot of... I'll go over that really quick. So Echidna is basically a lot more feature-rich than Foundry. It's been in development for years. So fuzzing, we can do things like fuzzing for high gas consumption. Echidna also works with any compilation framework. So let's say, for example, you don't want to use Foundry specifically. For whatever reason, you want to use Hardat or Truffle, then Echidna is compatible with those. Also, Echidna has a lot of different APIs for testing. There's like assertion properties, as you can see here, but there's also like Boolean properties. You can even test it in like DAP test or Foundry mode. And but one thing to know is that Echidna supports a lot of the HEVM cheat codes, just like Foundry, but some of them are not supported. Like, for example, Prank is not supported. I hope that answers your question. That being said, let's continue. So we have this test swap function. And what do we want to do? Well, we want to test it, right? So how do we do that? We'll go to a terminal. Let's go into the part of the directory. Let's do Echidna test. The contract that we need to test is Echidna test, and the config would be contracts critic config.yaml. Go ahead and test. Okay. So we're going to just test our contract. This is just testing it with 10,000 fuzz runs. It'll take a while, but if we do this, we'll see that the test passes, or hopefully it passes. Let's see if it fails. I'll wait a bit more. All right, I know let's just wait a bit till it hits 10,000 now. And it says it passes. So this may give us some guarantees that we're not able to game the swap function, but to be 100% sure, let's go and check the coverage. So it's going to be saved in this corpus file, and we can look at this covered.txt. And let's look at where it hits. So R means that the fuzzer reverted. However, there's a star, so Echidna was successfully able to hit this line. And this is just the test provide liquidity. So as you can see, it does revert, but eventually figures out how to get past that. And all of our previous assertions and post conditions on providing liquidity hold. That's good. And let's look at this test swap function. So Echidna does revert. It eventually figures out how to make sure there is liquidity by calling test liquidity. Then we sync the pair, we do the call, and look at that. It hits this, and it asserts that the call should never succeed. So this assertion seems to always pass. Let's go and look at the pair. So the function that we need to look is the swap, and it should take in an amount. Where is it? I am. Hold on. Sorry about this. 1 second, please. Let's find where this guy is. Here we go. Okay, perfect. So this is the pair contract. Let's look at what was hit. So we hit the reentrancy guard, we hit the get reserves, we hit the transfer, we hit update successfully, we hit the mint fee, we hit the minting for liquidity successfully, and here we are at the swap. So let's look and see where Echidna gets stuck. So it manages to pass this required check. It manages to get the reserves, do everything. It gets the balances successfully. It transfers the tokens. None of those reverts. Right here. So it fails that amount 0 in it is greater than 0 and amount 1 in is greater than 0. Why does it fail? Well, let's think about this. This check says insufficient input amount, and exactly, we didn't actually put anything in, right? So it seems with 10,000 runs, we can have reasonable certainty. There's no way to game the swap function. There's no numerical edge case where you can call something with amount 0 out or amount 1 out, and you can actually get tokens out. So that's perfect. We did a very simple test on just testing the swap. But now let's see if we can come up with some more complex invariants. So this is one that was fairly simple to test. Another invariant we could test is that swapping decreases and increases token balances appropriately. What that be? I'll just give some clarification on what that means. For example, since let's say we're swapping token 1 for token 2, since we're giving token 1 to the pool, our token 1 balance should decrease. Since we're getting token 2, our token 2 balance should increase. Fairly straightforward. Another cool invariant we should have is swapping X of token A for Y of token B and back should give you the same amount of token A. This is called path independence, and you can think of it like if you do the same thing in reverse, you should get exactly back where you started. In practice, this may not be exactly true because of things like fees or rounding. However, it should be within a certain tolerance. And last, and maybe most importantly, the pool invariant should stay constant during swaps. Otherwise, tokens could be drained from the pool. So we have all of these invariants, and some of them may take like a little bit more computation and a little bit more legwork to test. For example, the swap function that we saw in the pair is actually fairly minimal, and we'd have to do a lot of computation to calculate what the output amount should be and things like that and transfer the tokens. So this is where the periphery comes in. The periphery is a set of contracts that interact with the core. Again, the core, that pair contract contains pretty much most of the logic of the core logic. That's why it's called a core. And the periphery is just designed to interact with the core. It provides safety checks and helper functions. And that's why we saw that comment. This low-level function should be called from a contract that performs safety checks. The periphery is are the set of contracts that actually perform the safety checks. So the periphery has two contracts that we're going to go over. We're going to go over the library and the router. The library mainly contains helper functions, for example, sorting tokens or calculating amounts in and out. Let's just go through that really quickly. So as you can see, the first thing is sorting tokens. This just basically sorts the tokens in a certain order. And it's, as you can see from the comment, it's used to handle return values from pairs. When we go through the router, hopefully this will become a little bit more clear. Another helper function is to get this thing, is this pair for helper function. Given a factory in the two tokens, we can compute the pair address, and we do this without making any external calls. You've noticed I've commented some of the other init code hashes out. This was because when testing, I had to modify the pair slightly, which changed the init code hash. Another helper function for getting reserves. What we're going to do is we're going to sort the tokens, we're going to get the pair, and we're just going to determine the reserve amounts. So we call get reserves on the pair, fairly straightforward. And here is where things are a little bit more interesting. So, for example, we have this quote function. We can see what the comment says. Given an amount of asset and some pair reserves, we get the equivalent amount of the other asset. And this would be good for before a swap when we want to get the price. As you can see, it's fairly simple. The price is just calculated as the amount times the reserve divided by the other reserve. And this basically represents the ratio. It's just a ratio of the reserves. That's how the price would be determined before a swap. However, during a swap, we're actually going to change the reserves. Since we change the reserves, we change the price. So during a swap, we actually expect the price to fall. And that's why we have this get amount out function. As you can see from the comment, it takes in an input amount of an asset and some pair reserves, and it returns a maximum amount of the other asset. So it's very similar. However, what we do is we account for the fee. So that's why we multiply by 997. Remember, there's a 0.03% fee. We're going to multiply this amount by the reserve out, and then we're going to divide it by the new reserve, which is the old reserve times 1,000 plus the amount with fee. So I'm going to stop here if there are any questions. We just went over a little bit, or a lot, actually. If there are no questions, I'm just going to continue then. So we have this get amount out, and then we have another function called get amount in. This function kind of does something similar. Well, it does the opposite. So instead of giving an input amount and checking how much you're going to get out, this one we're given an output amount and seeing how much we're going to get in. So it's kind of like the inverse of the function above. And then we have these two get amounts in and get amounts out. They basically just loop through pairs and do a get amount out calculation. When we go through the router, we'll see why we need this. So that was pretty much everything about the library. Now I'm going to start to talk about the router. The router, as you could guess, it routes trades. So the router actually provides the safety checks for the core contracts. It's in charge of transferring the tokens properly. And if you've ever interacted with like Uniswap through a wallet, and your wallet has API decoding, you might have seen something like router.swapExact tokens for tokens. So you went through the router, actually. You didn't call the pair contract. You interacted with the router, and the router did all the state changes and called the pair for you. So let's go through the router's code. I'm going to ignore. This is just something that ensures that the deadline is bigger than the block timestamp, the constructor. These are functions for adding liquidity. I'm going to come back to these later. Same for removing liquidity. And we have this swap function. This is a private function. And this function, swap exact tokens for tokens, is what a user would call. There's also swap tokens for exact tokens, but for now, I'm just going to explain swap exact tokens for tokens. So let's look at what swap exact tokens for tokens takes in. Well, it takes in a amount in. That's how much we're going to input. Amount out minimum. This is the minimum amount that we expect to get out. The reason we have this parameter is just to protect ourselves against insane price slippage. So if the price changes too much and we get out less than the amount out minimum, the transaction will revert because we're not going to get as much as we want it out. Then we have this thing called a path. And what's interesting about the router is it can actually perform chain swaps. So for example, let's say you want to swap token A for token C. What would happen is you could swap the path could be you could swap token A for token B, then you could swap token B for token C. That way you swap token A for C, but you went through another set of tokens, in this case B. We're going to keep it pretty simple, so we can just imagine the path is just swapping token A for token B. So the path is just the address of token A and the address of token B. We also have this to address. This is who we're going to send the tokens to, and some deadline for how long the swap should take. Then let's look, we're going to return an array of amounts. What is this amounts? Well, we're going to go to the library and we're going to call get amounts out. So let's go back to the library and look at it really quick. The library performs chain get amount out calculations on any number of pairs. So it's going to take the paths, it's going to iterate through them, and then it's going to compute the amount out that we need on each of them. So let's go back to the router. We can see that this get amounts out basically calculates the amount out that you would get from every single swap on every single pair. In our case, it's very simple. We're just swapping token A for token B. So the get amounts out will just be how much we're going to get out from the first get amount out calculation. We're going to make sure that the last amount is bigger than the amount out minimum, because this is the amount that we expect to receive after every single chain swap. If that has to be bigger than the amount minimum to protect us from slippage. And then we're going to use this safe transfer from, which takes in the first token that we want to swap for, and we're going to transfer it to the pair contract. We're going to transfer the amount out that we need. And this is something we didn't do when we interacted with the pair directly. This transferred our token to the pair. Then we're going to call this internal swap function right here. So before I talk about the private swap function, are there any questions? Uh, 1 second. Okay, the toggle word wrap. Okay. Shift P. Okay. I should have enabled word wrap, but I think I'm having some technical difficulties on that, so I'm just going to continue. So we have this this private swap function. As you can see by the comment, it requires that the initial amount has been set to the first pair. Well, that's what we did in swap exact tokens for tokens. As you can see, we call this transfer helper .safe transfer from, and it transferred the tokens to the pair. So what is this swap function going to do? Well, it takes in the amounts that we calculated from get amounts out. It calculates the path that we provided as data here, and it calculates who we're going to send the tokens to at the end. So for every basically address in the path, what we're going to do is we're going to grab the input and the output, which are the two tokens in the path. So in our case, it's just going to be the input will be token A, the output will be token B. But if you had a bigger path, it would do this for every single one of them. So for example, A to B, B to C. Then we're going to sort the tokens. Here we need to sort the tokens because when we sort the tokens, here when we provide the path, it's done logically. Like for example, A to B, B to C. But the tokens that are actually sorted are in this ascending order based on their address. So once we get that token, we're going to get the amount out, which is the amounts in the amounts array. Then we're going to check if the input is equal to token 0. If it is, then the amount of the first token we should get out is 0, and we should get out the amount of the second token. So if this is the case, as you can see, amount 0 out will be 0, amount 1 out will be the amount out in the amounts array. Otherwise, we're going to do the opposite. Then we calculate the to address, and this to address, if our pair is just, like 2 tokens, just a simple swap, it is going to be the address that we want to the receiver of the tokens. Otherwise, we're just going to compute the pair and send and do a swap on the next pair. So in our example, when it's from A to B and B to C, the first pair, we're going to send it to the B to C pair. And then we're actually going to get the pair from the library, and we're just going to call that swap function that we know and love in the pair. So that was a lot to take in. Are there any questions about this? There are no questions. That's awesome. So we have seen swap exact tokens for tokens and the internal swap function. I'm going to briefly talk about swap tokens for exact tokens, but as you could guess, it kind of does the opposite. Instead of giving an amount in and getting something out, we're going to provide how much out we want, the minimum amount that we're willing to put in, and it more or less does the same thing. It just calls get amounts in, transfers everything, and calls a swap function. There are other functions in here, like, for example, swapping ETH for tokens. If you remember, Uniswap v2 works on swapping ERC20 tokens. So what you would need is you would need to take your Ether, wrap it, get wrapped Ether, and then do the same things that we just talked about. I'm not going to go into that too much, but I'd encourage everyone to play around with doing some wrapped Ether tests after the workshop. And yeah, so we explained pretty much the swapping function in the router. So we can go back and look at our swap invariants. Now that we have the router that will basically help us to do a lot of these calculations, we can actually test some of these invariants. So I'm not going to test the path independence invariant. That's a little bit more complicated. Again, after the workshop, I'd highly encourage everyone to give it a stab themselves. But for now, let's just test the other 3 invariants. So what I'm going to do is I'm going to go to part 4. Well, I'm going to click on it. And I'm going to go to the contracts. I'm going to create a new folder called critic. Inside the critic folder, I'm going to create setup.sol. And we can just reuse more or less the same setup that we had last time. Find it somewhere. All right, that's no problem. I can just go here. So I can copy all of this. I can paste it into the setup that we have here. So we can reuse most of this. However, there are a couple things we'll need to change. Firstly, we're going to need the library. So let's import that guy. Then we're going to import the router because we need that. Oh, I need a dash there. It should be Uniswap. Awesome. So we have everything we need. Now that we need to add the router to our setup. So, and we need to initialize it in the constructor. How are we going to do that? Well, let's look at the constructor of the router. It takes in the factory address and the wrapped ether address. Or let's just say we're not going to test. You don't need to test for now. So we don't need a test wrapped ether. That's why I just made it the 0 address. Also, we need to call this new. To be a semicolon there. Perfect. So we've initialized the router. There is one more thing we need to do. Because the router is an external contract and it's going to pull our ERC20 tokens from the user, what we can do is we have to give the router approval, because the router shouldn't just take our tokens without any approval. So I'm going to create a function. I'm going to call this do approvals. It's going to be internal. And as you could guess, it should do approvals. How are we going to do that? Well, that's going to do user.proxy address test token 1. Going to call the test token. What are we just going to call it? We're going to do abi.encode with selector test token approve.selector. Arguments we need, well, we need to call approve with a contract to approve and an amount that we're going to give the approval. The contract will be the router, and let's just make the approval the maximum that we can for testing purposes. Likewise, we need to do the same thing for the second token. The router, that's how you spell. And the amounts are going to be the same. Perfect. So we have this do approvals function, very simple. It just approves the router contract for the maximum amount. Now that we have that in our initialization, we should also approve it once. Okay, the linter, calm down now. Perfect. So that is pretty much all the additions that we need to make to the setup. Are there any questions? No questions. Fantastic. I'm going to continue. So we have our setup done. What's the next thing we need to do? You guessed it. We need to create a file that tests it. I'm going to call this Echidna uni v2 tester.sol. What do we need to do? Well, as usual, declare the solidity version. And then we're going to import what we just set up. Cool. And then contract tester is. So first thing we want to use the router to test a swap. But remember, before we can test a swap, we need to provide liquidity. So for now, what we can do is we know how to provide liquidity directly using the pair contract. We can just go grab what we did with the pair and just copy this test. Come on. So we have the same test provide liquidity that we wrote. We're just going to use this to provide liquidity, and Echidna should figure out that it needs to call this function first before we can do a swap on the router. And now that we've done that, we can actually start to write a test with the router. So how do we do that? Well, first thing we need to do, as always, is declare a function. Test. Should I call this function? Probably just something like, hold on. Test swap tokens, because that's what it's going to be doing. It's just taking the swap amount in. That's how much we want to provide to the contract. Let's call it public. What should we need it to do? Well, we're going to need some preconditions. Hopefully you're familiar with this pattern by now. What should the preconditions be? Well, if we're not complete, then let's call init. We can just call swap amount in swap in. Now that we've done that, let's go back and look at the pair, or the router, sorry. What do we need if we want to call swap exact tokens for tokens? Where are you? Here we are. Swap exact tokens. Swap exact tokens for tokens. We're going to need an amount in. That's what we're providing as a parameter to Echidna. An amount out minimum. I guess we could just set that to 0 for testing purposes because we're not going to be affected by slippage. We have a path. What should the path be? Well, let's go back and think about this. Let's just say we wanted to swap token test token 1 for test token 2, then our path would be the address of test token 1 and the address of test token 2. So let's write that. Address memory path. That should be equal to new address array of length 2. Remember, the path can be arbitrarily long. You could test a very long path to see if anything happens. But for now, we're just going to keep it simple and just use a path of length 2. The first entry in the array should be the address of test token 1. Second entry in the array should be the address of test token 2. Then what we need now is we need to have the previous state. And because we want to test that, like in all our other tests, against the state after the call. So let's go ahead and grab that. What do we want to test? Well, if we go back, we want to test that swapping decreases and increases token balances. And we also want to test the pool invariant. So what we could do, the previous state we would need is we would need the balances and the reserves before. So let's go ahead and grab those. So these are the two previous balances that we have. And if we have to realize here that in order to actually call a swap, we need to make sure amount in is between our 1 and our previous balance, because otherwise the call will always fail because we can't swap more than what we have. So let's constrain that. First, we need to make sure that previous balance 1 is bigger than 0. This way, we actually have some tokens to swap. And now that we have that, we can constrain swap amount in to be equal to between. Remember that helper function that asserts something is in between a certain range. Well, the value we need to take in is swap amount in. The range we need to take in is going to be between 1 and the previous balance. Cool. I'm going to keep going and check if there are any questions in a little bit, but for now, let's just finish the preconditions. We're almost done with these. We have the previous balances. The next thing we need to get are the reserves. So I'm going to call this reserve 1 before and reserve 2 before. How are we going to get them? Well, remember how I said there are a bunch of helper functions in the library? As you would guess, we have this beautiful helper function right here, get reserves. Given a factory and the 2 tokens, it'll give us the reserves we need. So let's use that. Factory address should be the address of the factory. Factory. Token A should be, that's not what I want. Token A should be the address of test token 1. And token B should be the address of test token 2. Cool. So we have these 2 reserves, and we want to get the K before. So what would K before be? Easy. It's going to be the product of the reserves. And remember, these guys are both uint 112s. When we multiply a uint 112 by a uint 112, we're going to get a uint 224. That fits into 256 bits, so it won't overflow. So these are all of our preconditions. Now I'm going to see if there are any questions. So there is a question. So are you using provide liquidity test to set the corpus? The answer is kind of. So Echidna does perform stateful testing. And so what Echidna will realize is that if it calls provide liquidity test swap, it'll get more coverage of the target code. So without a test for provide liquidity, there's no way for Echidna to actually test the swap because there's no liquidity in the contract, right? Unless we explicitly provide the liquidity first. However, in as we said in the previous parts, that to make we want to kind of make our test more modular. And now we're testing liquidity provisions and swaps in a more elegant way because Echidna will realize, oh, let's go back and just check. It'll see that we need that there is liquidity in the pool, right? In order to do that, The only way Echidna will get more coverage is if it calls test provide liquidity, asserts all the liquidity provision invariants are true, and then it can call test swap. I hope that answers your question. If there are no more questions, I'm going to continue. So we have all our preconditions done. Let's do the call. What should the call be? Well, as usual, we're going to take in a Boolean that represents success. And we are going to say usual user.proxy. Well, we're going to call the router this time because we're testing with the router, not the pair. And the data we're going to use is abi.encode with selector. So we're going to do router.swap exact tokens for tokens.selector. And now we need to think of the arguments. So let's go back. Let's look at what arguments the router will take. An amount in, that should be swap amount in, amount out min is 0. The path is what we created. The to address should be the address of the user. And the deadline, for testing purposes, we can just make that arbitrarily long because we don't really care. So let's type everything I just said out. We're going to do swap amount in. The amount out minimum is 0. Don't do this unless you want to get wrecked by slippage. But since we're testing, it's okay. We're going to take in the path that we provided. 2 should be the address of the user. And the time limit should be as long as we want. Cool. So now that we've done the call, we should think about our post conditions. So if the call was successful, what should hold? Let's think. Well, we have these invariants and we have our previous state. So let's check the balances and let's check the reserves after, because now we need the state after the call, right? So we went after val1 is going to be equal to test token 1 balance of. So these are the balances after. We also need to get the reserves after. Same exact thing as usual. We're going to provide the factory address. Let me scroll. And token A is just going to be the address of test token 1. Token B is just going to be the address of test token 2. Then K after should be reserve 1 after times reserve 2 after. Perfect. Now we can actually start asserting stuff. So let's think, what should we be asserting? Well, we gave test token 1 to the pair, and we're getting out test token 2, right? So one thing we could assert is that the previous balance of test token 1 should be bigger than the after balance of test token 1. So test or token 0 was updated correctly. Likewise, we can do the opposite for test token 2 because we are getting test token 2 from the pool. So previous balance 2 should be less than after balance 2. This should be token 1 was updated correctly. And lastly, we need to check that the pool invariant stays constant during swaps. So let's do assert k before is equal to k after. So these are our post conditions, and let's go and test them out. So I need to go into the part 4 directory. Let me pull this up and make it bigger. Then I need to do Echidna test. The contract we're going to test is Echidna v2 tester, and the config. Oops, I almost forgot. We need a config file, don't we? So let me go into critic, create a config.yaml, and we can just reuse the same exact config that we had in part 3 because we're doing the same thing. We're still using assertion testing. Awesome. So now let's try and see what happens. So I'm going to see if there are any questions in the meantime. Oh, what? Okay, well, first let me take some questions. There are no questions. But it seemed as though our test failed for some reason. Why is that? Well, one thing that's useful when seeing that a test fails and debugging it is the emission of events. So what I'm going to do is I'm going to go back here. I'm going to create an event. Let's call this event log uints. And what it's going to do is going to take in a uint number 1, and it's going to take in a uint number 2. So we can go to our test swap tokens, and let's just emit that event. I'm not sure what should be failing. So let's just say that K before and K after are what we want to check for now. As we debug, we can check other things. So we added that event. Let's go back to the terminal, run what we needed to. Oh, it fails. Let's see. Why does it fail? I think I can't make my terminal bigger to see the actual event. That's unfortunate. However, all the code is on GitHub, so I'd encourage everyone to try this themselves, and you can actually see the events. My terminal is a bit too small, unfortunately, so that's problematic. However, you'll see that when you do hit this log uints, you'll actually see a K before and K after. And I have a confession to make. I lied to you guys. This invariant should not be true. Why is that? Well, let's go back all the way to this picture right here. And as we can see, there's a 0.03% fee. Where does that fee goes? It goes towards the liquidity providers. How does it do that? By increasing K. So if we actually calculated everything correctly, this should not be true. K before should not equal K after. K after should be bigger because we added the fee back into the liquidity pool. So these reserves should change. And now we can do this. And let's see if this holds, hopefully. So I'm going to do the same thing. And so far, so good. Echidna probably won't find an error in this. Hopefully, we'll see. But since it didn't find the error immediately and it reused the corpus transactions, it means that the transactions in the corpus don't have the same property. So it seems that the invariant K before should be less than or equal to K after should hold. I'm going to pause here if there are any questions. Awesome. So because of time, I'm not going to go in and inspect the coverage. However, I would encourage everyone to do that. And we've successfully done a test from basically calling the router contract to interacting with the pair. And we can see that so far, everything is so good. So let's go back to where we were. Now, let's talk about the liquidity invariants. Now that we have the router, we can actually do the same test that we did, but with the router. So the invariants we should check are that providing liquidity increases the invariant, the same invariant we checked last time. And we can also check that LP tokens are minted either proportional to the pool share or proportional to the square root of the tokens. Another invariant that we could check is that providing and removing liquidity should give you the starting amount without fees. This is kind of like path independence, but for LPs. There are some rounding errors to account for. And another invariant we could test is that removing liquidity decreases the invariant. So let's go back to the router and let's look at how the liquidity provision works. So as we can see, where is it? We have this add liquidity function. It's external. It takes in two tokens, token A and token B, takes in the amount A and B that we desire, the amount B, A and B minimum that we're expected to get out, who we're going to mint the LP tokens to, and some deadline. So first thing it does is it calls this internal add liquidity function. Where is that? That's right up here. It takes in more or less the same parameters. And let's look at what it does. So first thing we're going to do, if the pair doesn't exist, we're going to create a pair. So this way, we don't actually need to create the pair first. We can just check if it exists and create it otherwise. Then we're going to get the reserves of the pair already. If the reserves are 0, this means that there's no liquidity minted yet. Then the amount A and the amount B that we're going to get out are just what we desire. Otherwise, what we're going to do is we're going to call that quote function. We're going to get a certain price back out. And we're going to make sure that the amount that we get are, first of all, are bigger than the minimum amount that we desire. And we're just going to return those amounts. So this liquidity function creates the pair and just makes sure that we're going to get out more than the minimum amount that we want. Then we get the pair, and here's where we actually transfer the tokens. As you can see, it calls transfer helper, safe transfer from. It transfers token A to the pair. It transfers token B to the pair, and it just calls the same minting logic on the pair that we know and love by now. So now that we're already playing around with the router, let's rewrite our test provide liquidity. But instead of using the transferring tokens ourselves, let's just use the router. We know this test provide liquidity on the pair works. Let's see if there's any bugs between the router's interaction with it and the pair contract. So I'm going to pause, see if there are any questions. No questions. So our preconditions are mostly going to be the same. Actually, pretty much all of them should be the same. The only thing we don't need is we don't need to transfer tokens ourselves. So let's remove these. And instead of calling on the pair, we can actually use the library now. So I'm going to change this to being, instead of pair.getReserves, this should be, I'm going to swap v2 library.getReserves. Remember, getReserves takes in the factory, takes in the one, and the address of test token 2. I mess up somewhere. There should not be a comma here because this just returns the reserves. K before it can be calculated the same way. And the nice thing about playing with the router is we don't need to transfer the tokens ourselves. The router has a helper function that add liquidity that'll take care of this for us. So we don't need this. In fact, we can just remove it at all entirely. And we need to edit the action because here we're not going to call the pair contract. We're going to call the router contract. We're not going to call mint on the router. What are we going to call? The selector will be router.add liquidity. That's not what I wanted. Liquidity.selector. And what do we need to put in? Let's go back, look at the router, see the parameters. We need token A, token B, the amount that we desire, the amount minimum. So let's go ahead and do that. So the first thing that we need to notice is that we need to put in the address of the tokens. So let's go ahead and do address test token 1. There should be a parentheses there. Address this way. Test token 2. We have the two addresses we need. And remember, we're going to be calling this with amount 1 and amount 2. So let's just say amount. Let's go back to the router. We want amount A desired and amount B desired. Let's just call that amount 1 and amount 2. Next thing we're going to do is the minimum amounts. Again, for testing purposes, let's just call them both 0. We're going to send them to the user, and we need a deadline. Again, let's just make that deadline as long as we can for testing purposes. Awesome. And let's look at our invariants. They should be the same. However, here we can again just call on the library instead. We paste this. And we don't need a comma here. And that should all work. Cool. And the liquidity invariants that we're going to test are the exact same. So now let's just see that if we test this with the router, everything goes smoothly. So right here, while the fuzzer runs, I'm going to pause, see if there are any questions. Awesome. So it seems that we can test liquidity both on the pair and through the router. And so far, there don't seem to be any bugs. I'm going to stop this in the interest of time. But again, the code is on GitHub. I'd highly encourage everyone to play around with it themselves, get a feel for Echidna, look at the coverage, see what was hit, what they could improve on, write their own tests. But let's get back to the LP invariants we have. We want to test that. We tested adding liquidity, but what about removing liquidity? We should be able to test that removing liquidity decreases the invariant, removing liquidity decreases the LP token balance, and that the token balances of the LP should always be monotonically increasing. This is more of a system-wide property, actually, but for now, let's just implement a test to remove liquidity. So let's go here. I'm going to call this function. Call it, I don't know, maybe test remove liquidity. And what should this take in? Well, let's just take in the LP amount that we want to remove. It's going to be public like everything else. And hopefully everyone knows we're going to have some preconditions. What should the preconditions be? Well, first thing we should do is we should, this time, the only way we can burn these tokens is if we had tokens and provided liquidity to begin with. So let's grab the balance that the user had before. I'm going to call this pair balance before. It's going to be the test pair dot balance of the user. And they have to have liquidity to burn. So, or they should just be not test pair, but pair. I don't know why I typed that. We're going to require that the pair balance before is greater than 0. This way, they actually have tokens to burn. The next thing we need to do is we need to constrain the LP amount, just like we did with when we were swapping. We need to make sure that you can't burn more than your balance. So we're just going to constrain it. We're going to get the same state that we need last time to test the pool invariant. How are you going to do that? Well, you went reserve 1 before. Reserve 1 after. This should be equal to library.get reserves. Take in the address of the factory. And we're going to take in the address of the same tokens that we had. be anymore. Yes, these are not used, but I'm going to create the same exact thing K before. So in the interest of time, I'm actually not going to get the balances, but I'd encourage everyone to play around with the user balance and test this invariant that the token balances should always be monotonically increasing. Let's think about this for a second. We're going to have a balance of token 1 and token 2, and even though we put them into the pool, when we get them back out, we should always get at least the same amount that we put in or more because of the fee. So there should never be a situation where the balance of test token 1 and the balance of test token 2 is going down. Another thing we need to do is we need to approve the LP tokens for the pair or for the router to take them. So I'm going to do user.proxy. We're going to have to call the pair contract. Remember, the pair contract is an ERC20 token. So what are we going to call? We're going to call, well, first let's create the data, pair.approve.selector. Well, what are we going to approve? We're going to approve the router. And for testing purposes, we're just going to approve amount. So we need this to be successful because otherwise the call will never pass if we don't approve them. So I'm just going to require success 1. These are all of our preconditions for liquidity removal. And before I do the call, I'm going to check if there are any questions. No questions? Sweet. So let's do what we always do by now. We're going to take in a success variable that returns if the call was successful, and the same pattern as always, user.proxy. Let's think for a second. What are we going to be calling? Well, we're going to be calling the router. And what is the data we're going to need? Well, we're going to be calling router.remove liquidity .selector. And let's go back and look at how liquidity removal works in the router, because we need to be able to call it with the correct parameters, right? So we have this remove liquidity function. It'll take in token A, token B. It'll take in the liquidity amount that we want to burn. And these amount A and amount B mins are going to be the minimum amount of token A and token B that we want to get back. So the router actually protects us from slippage when we remove liquidity, because that is also affected by things like sandwich attacks, and we could get less than we expect out. So that's why we have these amount A min and amount B mins. We're going to take in a to address as usual and the deadline just to make sure the trade happens a certain number of time. And as you would imagine, removing liquidity kind of works in the opposite way of providing liquidity. We're going to grab the pair. We're going to actually transfer our liquidity tokens to the pair, and we're going to call on the pair burn. So this way, we transfer our liquidity tokens and the pair will burn them for us. If we go to the pair contract, we can look at this. Where is it? Burn function. What it does is it takes in the reserves. It takes in the token balances that we have. It calculates the liquidity. So this is the amount of LP tokens we sent to the pool. We're going to basically see how much we're going to get out, and we're going to burn those liquidity tokens that we sent. Then we're just going to transfer the liquidity, or the underlying liquidity, amount 0 and amount 1, to the to address. So kind of like the opposite of what happens when we provide liquidity. The key thing to note is that we transfer tokens, our liquidity tokens, to the pair, and the pair will burn them for us. Then we will get, when we get the tokens back, we just make sure they're bigger than the minimum. So we know the parameters the remove liquidity token takes. Let's go ahead and use them. So the arguments here should be the address of test token 1, the address of test token 2, How much are we going to burn? Well, the LP amount. The minimum amount in this case will still be 0 just for testing purposes. We're going to send that to the user. And the deadline, as always, will be as long as possible, which is the maximum uint. Cool. So that was our call. And before I talk about the post conditions, I just want to see if there are any questions. Okay, moving on. Let's look at our post conditions. So if this call was successful, what should happen? Well, as always, let's get the state after the call. So I'm going to call this pair balance after. We also need the previous reserves. This should not be this before. Why did I call this after? I do not know. But this should be reserve 2. Or should be reserve 2 before. Should be reserve 1 after. This should be reserve 2 after. And that should be equal to the library.get reserves. I can just copy this. Why can you not scroll? Hold on. There we go. Let's copy this. That should be correct. And then we need to get k after is equal to reserve 1 after times reserve 2 after. And now that we have the state after, we can start asserting stuff. So what should we assert? Well, the first thing is that removing liquidity decreases the invariant. This is because if we remember, the invariant or the pool invariant is x times y equals k. If you lower x and you lower y, then k should also be lowered. So let's assert that. Next thing this is invariant should decrease. Next thing we should have is that the pair balance before should be bigger than the pair balance after. Why? Well, we burned liquidity tokens, right? So removing liquidity should decrease our LP token balance. And because we don't have much time, I'm not going to test that token balance should be monotonically increasing. However, I would highly encourage everyone to test that property after. So let's go ahead. Now that we have our post condition set up, let's do the usual. Let's run Echidna. So far, so good. Echidna doesn't seem to find any issues. I'm going to pause for questions while we let the fuzzer run. Okay, so moving on. I'm not going to let this run in the interest of time, but what I would encourage everyone to do is this code is on GitHub. You could use it as a template. We have a lot of invariants that we tested today, but also a lot of invariants I mentioned that we didn't get the time to test. So I'd encourage everyone to play around with the templates, see what they can add, see how they can use the router in more and more creative ways. And that's going to be your homework this week. I want everyone to test more invariants and write system properties. Anish talked about property mode. If you haven't seen those videos, I'd encourage everyone to check them out. But now that we have some kind of tests about operations, like, for example, providing liquidity, removing liquidity, swapping, we can create properties for the global system. Like, for example, K should never decrease. And we can use Echidna in property mode to assert that those are true. So I would encourage everyone to think about these global system properties and write your own tests and make PRs to our repository. That way we can go and give some feedback on the tests. And yeah, I hope everyone learned a lot. I hope everyone had a lot of fun with this workshop. This is going to be the last time that you see me next week. I'd encourage everyone to attend the next workshop we have. You're going to learn a lot. It's going to be amazing. And yeah, I hope that everyone enjoyed this.